I will introduce our last speakers in this session. The first one is Edwin Hancock from Computer Science University of York and from Beiyang University. And then it will be followed by Francois Lewis from Computer Science at the University of Copenhagen. So please be aware that there will be a photo, a group photo on Zoom. So if you miss the first picture this morning, you have another chance to join the group. So let me then introduce Edwin Hancock, who will speak about shape from polarization.
Okay, so what I want to do in the next 45 minutes is to try to explain how polarization vision can be used as a tool for not just recovering the shape of objects, but also probing their surface structure and understanding of the composition of the materials from which they are constructed. So the people I have performed this work with over a long period of time, about 15 years, are Gary Atkinson, Will Smith, Nitya Subramanian, Guli Salman, Li Chi Zhang, Sylvia Tozer, Hardy Darlan, and Dijong Zhu. So hang on, I'm just having difficulty scrolling forward. So this is the outline of the talk. What I'm going to do is to spend some time motivating and explaining the background for polarization vision, particularly in the context of newly available polarization cameras, and explain some of the capabilities of polarization vision. And I'll talk a little bit about the basic physics that underpins it. And I'll then talk about some very, very old work that I did in about 2006 with Gary Atkinson, because it establishes the foundations of what I'm going to talk about. And then I'll spend some time talking about more recent work that I did with Antonio Robles Kelly at ANU on spectropolarimetry, that is to say, using polarization images captured at different wavelengths to probe the refractive indices of the surfaces of objects. So let me start by motivating the work by telling you a little bit about polarization vision and what the capabilities and potentialities are. So polarization cameras are now becoming more widely and more cheaply available. And if you can collect polarization images, then a number of things that you can do. You can, as I will show you in this talk, you can recover surface shape, and particularly you can recover the shape of transparent objects, because polarization vision is sensitive to changes in refractive index. You can probe the surface substructure of objects, and this becomes very useful. For instance, if you're looking at surfaces which have a layered structure like skin, or the surfaces of biological materials like leaf. And the applications of polarization vision include things like imaging in bad atmospheric conditions, underwater imaging, and directly measuring the surface properties, such as refractive index. And in addition to being susceptible to machine vision approaches using polarization cameras, polarization vision is used by many animals and particularly aquatic creatures and insects to help them navigate and also take advantage of the environment in which they live. I'll tell you a little bit more about that later. So here are some examples of polarization images. What I'm showing you here is the degree of polarization. I'll explain how that can be computed later on. And these images were taken with the Ricoh camera. And here you see there's a transparent object overlaying a grid. And if we look at the degree of polarization, then the transparent object is revealed. And here again, you see an image of a bottle in visible light. And if we image that using degree of polarization, more structure of a scene is revealed. Here's another example looking through a grid, a transparent grid on the surface, and revealing the writing underneath. If we take this into the wild, then some of the applications become very, very clear. So this is an image of a car in a scene containing natural vegetation, and then in degree of polarization reveals the reflective surfaces very clearly. And so that's obviously very powerful if you want to image objects through camouflage. Here's another example taken through the front window of a motor car, and in degree of polarization reveals the passengers, whereas without invisible light, that's not possible. So what can a polarization camera measure? Well, it can give you a number of representations. I'll tell you about that later on. But basically, it allows you to measure the degree of polarization, the phase of polarization, and the mean intensity of pixels in an image. And it's then up to your wit as to how you use those pieces of information to develop surface analysis and shape recovery algorithms. So, does the light source need to be polarized for us to do this? Well, the answer is no. Actually, as I'll show you later on in this talk, when unpolarized light crosses a boundary between surfaces of different refractive index, then it acquires a degree of polarization. This is basically due to splitting of the light by the surface, and we can exploit that fact to recover degree of polarization. And as I'll show you from that, you can recover things like the direction of the surface normal at a point on the surface, and also the refractive index of the surface. So, how complicated can polarization vision become? Well, I'll show you some examples in this talk, but if we have a single polarization, then if we know the refractive index of the surface we're looking at, then we can recover a surface normal and hence the 3D shape of the object through surface integration. If we have multiple polarization images, that is, say, taken from different viewing angles or different light source direction, then we can recover a lot more. We can recover shape, refractive index, albedo, and as I say, intrinsic surface texture. One of the things I'll talk about in this talk is something called spectropolarimetric imaging, where we take polarization images at different wavelengths. And if you have such data, then you can recover shape, albedo, and refractive index at different points on the surface and different wavelengths. So let's just show how powerful polarization imaging can be. This is an example of a reflectometry analysis from a scene containing natural leaves and plastic leaves. What I've done here is I've plotted the normalized pixel intensity versus the degree of polarization. And you'll see that for natural leaves and plastic leaves, those distributions are very different. And what that means is that we can use that property to segment and to differentiate the natural leaves and the plastic leaves. And here's an example of doing that. So polarization images basically can allow you to detect different types of surface within an image, as well as recovering the shape of those objects. So what about polarization vision in nature? Well, there is evidence that both insects and aquatic creatures, that is to say shrimps, crabs, cuttlefish, exhibit to varying degrees polarization visions. And there are certain creatures that have up to 16 different channels capable of detecting different orientations of the polarization of light, which they exploit in their environments for things, for instance, like navigation or viewing transparent objects. Okay. So most animals actually lack optical polarizing filters of the sort you might use in a camera or in the laboratory, but instead what they have are individual photoreceptors sensitive to different orientations of polarized light. So here's an example of where polarization vision might prove to be a big advantage. This is underwater vision, and what we have here are images taken with different phases of polarization. and you notice that those reveal different facets of the scene and allow you to image through what is otherwise a murky environment. Here's another image. This is an image of a transparent creature. I think this is a jellyfish. And what I've shown here is the degree of polarization. And because the degree of polarization is sensitive to the refractive index of the material through which light passes, that allows us to distinguish between this transparent object and its background. And so, for instance, various creatures, for instance, the mantis shrimp, which I've shown you here, and which has the most beautiful eyes you could imagine, with not just individual sensors, but individual sensors orientated in different directions. A mantis shrimp could potentially see that transparent object because it will be sensitive to changes in refractive index, hence changes in degree of polarization in the aquatic environment in which it lives. So these are just publications that I'm going to use in this talk. You can look them up later. The literature on polarization really started in the early 90s with people looking at the first attempts to use polarization in poor atmospheric conditions and for various machine vision applications. And then in the early 2000s, it really picked up momentum with people developing shape from polarization algorithms and looking at other quite sophisticated applications. And then quite recently, it has become very, very important in the graphics field, where people have used polarization for a whole number of quite demanding tasks. So for instance, things like transparent object reconstruction, polarimetric reflectance estimation, skin reflectance analysis, and even holographic virtual reality. So that's the motivation. That's why you might be interested in using polarization vision, potentially very powerful, used by in natural vision systems as well. And so what is the basic physics underlying polarization, which we can exploit to recover shape and also analyze surface composition? So this is really back to the classroom, back to physics. There are two types of polarization, linear and circular. In the case of linear polarization, the plane of the electric and or magnetic fields are confined to a particular direction. And in the case of circular polarization, that plane rotates as the electromagnetic wave propagates. So what are the origins of polarization? Well, when unpolarized light is scattered or passed through what is referred to as a dichroic medium, that is to something which will split the light into two beams, which can then interfere later, then the surface, the light develops a degree of spontaneous polarization. So what about the environment in which we live? Well, when sunlight leaves the sun, it is unpolarized. However, when it strikes the atmosphere, it undergoes something called Rayleigh scattering. That is to say, particles which are much smaller than the wavelength of the light scatter it, and that causes the light to develop a degree of polarization. And if you look at this plot on the right-hand side, that actually shows how polarization varies across the sky at a particular time when the sun's in a particular direction. And in fact, insects are known to use that pattern as part of their navigation. Okay, so when light is reflected from the boundary between layers of different refractive index, because of what I just said, it develops spontaneous polarization. So if we take light and consider the different things that we can do with it, we can transmit it, we can reflect it, and we can scatter it from a surface where the light is basically subsumed into the surface, scattered and then re-emitted. In each of these situations, a degree of polarization will develop. So how does the degree of polarization behave? What are the parameters that determine how strong the polarization of light is when it undergoes a scattering process that induces polarization? Well, it is first of all dependent on the angle of incidence of the scattered light, and secondly, it's determined by the refractive index of the scattering surface. So based on those two properties, if we know the relationship between polarization and angle of incidence, and also the refractive index of the surface, we can try to perform some kind of analysis to recover surface shape through the direction of a surface normal and surface composition through the value of the refractive index. Now here's a sort of a very old-fashioned laboratory setup that you might use to measure the polarization of light scattered from an object. I mean, now you would do this with a polarization camera, but you take unpolarized light, you pass it through a polarizer if you so desire. That light then scatters off the surface, and you can then analyze it by passing it through a polarizer, a linear polarizer, and moving that polarizer through different angles to analyze the degree of polarization of the scattered light. And to make things simpler, if you have access to a polarization camera, then in a similar way to a color mosaic, there are orientation mosaics in the camera, and those are sensitive to different orientations of the polarization of light and can read out, for instance, representations of the light polarization, including the Stokes vector. So having mentioned Stokes vectors, how can you represent polarization? Well, the simplest thing, and the thing I'm going to talk mainly about in this talk, is something called the transmission radiant sinusoid, and this it measures the mean intensity the intensity to pixel as you rotate a linear polarizer. And so as you rotate the polarizer, the transmitted radiance follows a sinusoid, and the amplitude of that sinusoid determines degree of polarization, and it also has a phase which you can measure. Quite often people work with different representations of the polarization of light. One of the most popular of these, which can be estimated directly from polarization measurements, is the Stokes vector. It distinguishes between different states of either linear or circular polarization, plus the unpolarized case, and it has a very convenient spherical representation, which allows polarization parameters to be recovered. There are also the Jones matrices, and these allow you to model the effects of the optical medium on fully polarized light, which is represented by a Stokes vector. And then there are Muller matrices, which additionally allow you to model the effects of an optical medium on the Stokes vector when you're dealing with randomly or partially polarized or incoherent light. So many different ways of representing polarization. Now, what I want to do in this talk is really to focus on different machine vision settings where we can use polarization to leverage the estimation of object shape and the surface properties, that is to say, refractive index of the surface. So if you have a single polarization image, you can estimate surface normals, provided you're in a situation where you have constant albedo and uniform refractive index. And in addition, you know the refractive index. If you have a single polarization image and a brightness image, then you can estimate normals, albedo, and variations in refractive index. Multiple polarization images will allow you to estimate directly the height, albedo, and refractive index. And if you have multiple polarization images at different wavelengths, that's a setting I will talk about later on, and fixed direction, then you can estimate surface normals, albedos, and a variation in refractive index. And this is referred to as spectropolarimetry. So just to underline the differences between shape from shading and shape from polarization. In shape from shading, you measure the brightness of the point on the surface, and that will tell you information about the angle of incidence of the light to the surface normal at that point on the surface. And when you have shape from polarization, your image, your polarization image, will tell you about the angle between the surface normal and the line of sight between the point on the surface and the camera. Okay. So let's talk a little bit about the theoretical background. Basically, this was all described by Augustin Jean Fresnel, working in the early part of the 19th century. And what he did was develop a simple model for the electric field components parallel and perpendicular to a surface when light undergoes scattering from that surface. So I don't want to go into all the details here, but the Fresnel theory allows you to compute various coefficients based on the electric field components and the angle of incidence and the refractive indices of the medium in which light propagates and then the surface from which it's scattered. And that allows you to work out expressions for the polarization in two different scattering cases. The first is when you have specular reflection from the surface. And here I've written down the expression for the degree of polarization that develops when a light scatters from a surface, making an angle theta with the surface, and where n is the refractive index. And if you plot that polarization versus angle of incidence, what happens is that you have the degree of polarization reaches a maximum at a particular angle of incidence. The position of that maximum depends on the refractive index. And this turns out not to be particularly good for estimating surface shape, because for any measured value of polarization, you have two possible incidence angles. Okay, so I said there that the position of the maximum depends on the refractive index, and here's a table which shows you some of the refractive indices of well-known materials. So the larger the refractive index, the stronger the polarization effects. The second and perhaps more interesting case is the case of diffuse polarization. Here the light is subsumed into the surface, undergoes scattering, and is readmitted at a particular angle theta, and there is a similar expression for the degree of diffuse polarization in terms of the refractive index and the emittance angle of the light, theta. And if you plot that curve, what happens is now there is only one emittance angle for each measured polarization, so it's more suitable for estimating shape, and the magnitude of the effect depends again on increasing refractive index. So the greater the refractive index of the material, the greater the measured degree of polarization. Okay, and this just shows how polarization changes as we vary the light direction. So what we're going to want to do is to make measurements of polarization from polarization images. And so if you have access to the transmission radiant sinusoid, then the difference between the maximum and the minimum intensity at a pixel determines the polarization. It's defined to be the difference between the maximum and the minimum divided by the total of the maximum and the minimum intensity. Okay, so that gives us a measurement of degree of polarization. Here's an example of a polarization image. We have the brightness, the phase of polarization, that is to say the phase angle of the sinusoid, and the degree of polarization. And here you'll notice that the degree of polarization is greatest near the places on the surface where the surface is inclined at the greatest angle to the camera or the observer. So let's just run very, very quickly through some single view shape reconstruction results. What you do is you acquire a polarization image, you estimate the zenith angle from a diffuse polarization and the degree of polarization measured. The azimuth angles only ambiguously determine the rotation of the surface normal about the camera direction. So you have to be able to disambiguate that in some way. And then once you have surface normal direction, then you can recover surface height by performing surface integration. And here we use the Hancock and Chalapa method. So you've seen the imaging set up before. What we have to do is for every pixel in the image solve this equation for theta. And so we have to know the refractive index in order to do that. And if we have the refractive index, then there's only a single solution for each value of polarization. And that allows us to estimate sine theta, the sine of the angle between the surface normal and the camera direction. And combined with the azimuth angle, that gives the surface normal direction. And from the surface normal direction, we can estimate surface height through surface integration. Okay, so here's some examples of the components of the polarization image. And now we see examples of the fields of surface normals recovered using the method I've just described. And here are surface heights recovered by surface integration. And for each of these objects, it does a reasonable job of recovering the fine surface detail. I should say this work is very, very old. These images were actually collected in a lab using a camera, a rotating linear polarizer, which had to be rotated by hand. There were all sorts of image stability problems. And if you tried to take these images now with a polarization camera, you would get much, much better results. Okay, so what I'd like to do now is just expand this picture slightly and talk about the problem of recovering shape and refractive index from multiple polarization images captured at different wavelengths. So what we need to do here in order to simultaneously recover surface shape, refractive index, and albedo is to put constraints on the way in which the imagery varies with wavelength. Particularly, we have to have a model for the wavelength dependence of refractive index. And we also need constraints on the integrability of the surface so that we can use the Francois and Chalapa algorithm to recover surface height from surface normals. So what I'm going to describe is an optimization method for doing this. And that optimization method is based on the ratio of the maximum and the minimum brightness at a pixel as measured by the transmission radiance sinusoid. So this equation is due to Wolf. The early work on machine vision using polarization, and they showed that the ratio of the minimum to the maximum intensity at a pixel as measured by the transmission radiance sinusoid is given in terms of the cosine sine of the angle between the surface normal and the camera direction and the refractive index eta. So if we can measure that ratio, we can set up an optimization technique to try to minimize the difference between the measured and the predicted values and to define our data closeness and hence recover surface normal direction, imposing constraints on integrability. Now, the ingredient we need to do that is to make sure that the refractive index behaves continuously with different wavelengths. We're going to have a series of images, polarization images. For each pixel, we have the polarization at a particular wavelength, and also we need to know the wavelength at which that image was taken. So there are a couple of models you can use for the wavelength dependence of refractive index. It varies by about 10 or so % over the visible spectrum. And the two models which are popularly used are the Cauchy and Selmayr models. We've explored using these in our method. So what we want to do is at each pixel, we want to allow the refractive index to vary with wavelength as determined by one of those two models. And we want to keep the zenith and azimuth angles of the surface normal fixed over the different wavelengths. So what we want to do in order to recover surface normal and refractive index variation with wavelength is to set up an objective function which measures data closeness. And here we do that by measuring the squared difference between the measured and predicted values of the maximum to minimum intensity ratio plus a smoothness or regularization term that ensures that the surface normal field is integrable. That is, it's pretty old hat. And then what we want to do is to minimize this with respect to the parameters of the Cauchy and Selmayr models of the variation of refractive index with wavelength. So this is the integrability constraint. It can be re-expressed in terms of the rate of change of zenith angle with position in X and Y on the image plane. And if I incorporate that form of the constraint, the cost function we want to minimize is the theoretical value of the ratio of maximum to minimum intensity given in terms of the angle of the surface normal and the wavelength and the theoretical value of that quantity. And we sum that over all wavelengths and over all pixels in the image. And then we add to that a term which enforces integrability on the field of surface normals. And that just depends on alpha, the azimuth angle of a surface normal, the rotation of the surface normal about the line to the camera, and theta, the angle between the surface normal and the line to the camera. And theta of y is the rate of change of that angle with direction y on the pixel lattice. Okay, now that can be actually turned into an equivalent minimization problem, which involves looking at the difference between the reconstructed value of the zenith angle of the surface normal theta and its predicted value as given by the measured ratio of maximum to minimum intensity and the value of the refractive index at a particular wavelength. Okay, so the solution to that minimization problem is given below, and that's how we iteratively update the zenith angle of the surface normal by integrating over all the possible wavelengths provided by the polarization images at different wavelengths. If we want to recover the refractive index, that means we have to solve the quadratic equation given here. Turns out there are two solutions to that quadratic equation, and what we do is we opt to take the solution which is most physically plausible, provided the solution is real, or failing that, we take the solution which is smoothest. So we iterate between estimating the angle theta and estimating the refractive index. Okay, so this is how the method works. We collect images with fixed viewpoints at different different wavelengths with different angles of the polarizer. We solve the minimization problems to estimate refractive index and zenith angles, and then we resolve potential ambiguities in the azimuth angle by imposing wavelength continuity of the azimuth angle. And then finally, we reconstruct depth using the Francophone and Chalapa Fourier domain surface integration method. So here's some examples of the types of results we get. So the object is shown in the image in the right-hand side. We have multiple polarization images over, I think, about 12 different wavelengths. And then you see the field of surface normals recovered in the middle column and the albedo estimated at the pixels in the image. Here another set of examples. And again, you get we get a good reconstruction of the surface shape and the surface normals. If we measure the ground truth versus reconstructed surface normal directions and measure the angle between ground truth and the reconstructed for images where we have ground truth in the form of range images, we're getting accuracy of about 10 degrees, and that the error increases by about 30% as we increase the angle of the light source to the surface. Here are some examples of the surface height reconstructed for those examples I showed you earlier. So good at reconstructing surface structure detail. And here I show representations of the refractive index. And particularly if you look at the pig at the bottom, you will see that the refractive index pulls out the different regions on the surface where we have different refractive index due to the difference between the glazing and the painting of the object. Okay, so let me conclude there. What I have done is demonstrated the potential use of diffuse polarization for shape recoveries from single and multiple polarization images. In all of the imagery I've shown you, the initial light is unpolarized, and it develops a spontaneous degree of polarization on scattering from the surface. By analyzing that degree of polarization, either using a single image or across different wavelengths, I'm able to recover surface shape. And in the case of multiple wavelengths, I can also recover the refractive index and its variation. And the recovery of shape appears to be fairly robust, and so these algorithms could be ported onto a polarization camera if you wanted to turn them into a range sensor. And not only that, that you can actually use this method to estimate the material characteristics of surfaces. And what I've concentrated on here is the real valued refractive index. There is also a complex version of the refractive index, which tells you about absorption and scattering when light interacts with the surface. And that is potentially a more powerful way of characterizing surface composition. And with a more complicated setup, complex refractive index can be estimated from polarization images too. So thank you very much for listening to me. And I think I've left 5 minutes for questions.
Sure, thank you very much for your great talk on polarization. So I don't see in the chat. No, I see one end. Sylvia. No.
I have one question, Maurizio.
Okay, go on.
Do you hear me?
Yeah. I do hear you.
Yeah.
Okay, I am Jean-Denis Duroux.
Okay, yeah, nice to meet you virtually for the first time.
Nice to meet you, yes, for the first time, yeah. Thank you for your talk. If I understand well, there is no such thing as the equivalent of uncalibrated photometric stereo, isn't it?
Well, I guess it depends what you mean. I mean, if you take a normal camera, then you have to calibrate the brightness response yes. So that you can estimate the parameters of the transmission sinusoid. it really depends what calibration parameters you're talking about.
No, I talk about the light illumination calibration.
Right, yeah. So you don't need to know anything about the brightness of the light source, basically because it's a relative measurement, and what you're measuring is the ratio of the difference in maximum minimum brightness divided by the sum.
So this is a big advantage compared to photometric stereo.
Yeah.
Okay. Thank you.
Other questions or comments?
Hello.
Hello.
You hear me?
Francois, yes.
Yes. Edwin, nice talk. At the beginning, you showed us a couple of pictures where you had transparent objects and that became essentially opaque and that you could recover with
well, it's not so much they become opaque. Let me explain. Perhaps I skipped over them too fast. Let's go back. Okay, that was the one. So what happens is from the formulas I showed you, you can see that the polarization, diffuse polarization, depends on two things: the angle of emittance of the light and also the refractive index of the material.
Yeah. And
so if this is an image of the degree of polarization, right? So it's not the image through a particular polarizer. It's the actual value of the degree of polarization.
But I think
the value of the degree of polarization depends on the refractive index. So that means as you move from one transparent material with one refractive index to another transparent material with a different refractive index, then the degree of polarization will change.
Yeah, and that's there that I would be interested because, and Jean-Denis knows it because he's with me on that, and Ivan too. We have small pieces of amber.
Right.
And we are interested actually in recovering both their content because they are insect fossils, but we would probably also need the shape of the amber itself. And
right. So
have any chance to be able to use this kind of techniques to be able to extract?
So I mean, this is a case basically of an object with variable refractive index embedded in a lump of amber.
Yes.
And you then pass light through the amber. So it's first of all, it's going to strike the surface between air and amber, and there's going to be some polarization developed there.
Mm-hmm.
That light will then pass through amber, presumably in a polarized state. It will pass through the insect, which we're assuming is transparent, and that will change the degree of polarization. Actually, the equations I've shown you here won't actually deal with that. You'll have to look at a more complicated case. And then the light exits the piece of amber, and again, that will change the polarization. So it's quite complicated, but I guess you could analyze each of the different scattering processes and work out what their effects would be on the degree of polarization. I mean, I suspect you will see the insect inside in the degree of polarization. Trying to actually understand what it means might be more complicated.
I would. The first thing I would be interested is first of all to see the surface of the amber.
Yeah.
To be in a clearer way that I would do. So to have an idea how to segment it, for instance, in a relatively precise way. And I mean, there would be. What you talked about transmission and reflection and Fresnel effects. They would be present also with amber.
Yeah. I mean, I would just take some images and see what they look like. Yeah. Compute the degree of polarization. I mean, it's multiple scattering processes are going to take place. So if you're trying to do any analysis, that might be a little bit intractable, or you'd have to put in some global assumptions. But the images might contain something which looks pretty.
Okay. Thank you.
I don't see other questions. I have one. So can you say something about uniqueness of this surface reconstruction? So in shape from shading with a normal light, there is a result, a theoretical result, showing that if you have a couple of images from two different points of view, then there is a unique surface corresponding to them.
So if we go to this equation, where is it here? I mean, if you're working with diffuse, if you're working with diffuse polarization, and say we start with light that is unpolarized, it is scattered from a matte object, it undergoes diffuse scattering, not specular scattering. Then the degree of polarization follows that equation. There is only a single value of theta for each measured value of rho polarization. So that's the good news. The bad news is there's an ambiguity about the azimuth angle of the surface normal. There are two solutions, and you have to find a way of resolving that. So, I mean, various things can be done, including basically looking for continuity.
Okay, but
so there's you get ambiguity through ambiguity in the azimuth angle of a surface normal is the short answer. If you try to do specular shape from shading, then things are worse, because for each measured value of specular polarization, there are two possible zenith angles. So you have probably a fourfold ambiguity.
Okay, I see. Okay, thanks again for the talk, and we can proceed with our program. The second speaker of the session is Francois Lewis from Computer Science at the University of Copenhagen. And this title is Variant Shape Priors and Optimization of Fiber Bands. Okay. So I see the first slide. So
yes, thank you for the introduction, and hopefully you can see my slides.
Yeah.
So there is, can you?
Yeah, sure.
Yeah. So
everything is okay.
Perfect. So I'm not really talking about 3D printing in that talk, though. Actually, I mean, from the moment I started to now, we are at this kind of things. Maybe you can see them. They are small models of human femurs that have been extracted from CT scans and printed in small models. So my talk will be about how can I use some shape priors or shape regularizers that would be invariant to some sort of pose in order to be able to segment objects, and that's in 3D images. So my applications there would be medical. And in order to do so, I will have to develop a couple of things, couple of mathematical concepts. So my original problem was not something with bones, but with brains. That was, I was asked by colleagues at the hospital close by the university to help them to segment some rat brains for some studies. So here you can see you have slices of MR images of rat heads. They are living rats. And things of you see here is a slice of a rat brain with some, and you can see skulls and other structures and relatively important variations in intensities. So the problem we have is that we have variations in shape and pose, we have a few examples, but even though we have variation in shape and pose of these objects, then they have still a similar appearance. And the goal was to be able to include some training knowledge in order to develop this segmentation problem and make it so that it would be invariant to pose and reasonable variation should be allowed. Invariant to pose because I could have small rats, big rats. Rats are put also in a mini MR scanner and their head could have a slightly different positions. That would mean a bit of rotation, translation of the objects. So I would like to build something that is sufficiently robust to that. So I went into the literature. And of course, I mean, you have a series of literature, mainly in 2D, by the way, that says, try to do that, use a classical variational approach where you have some data term that would describe what you see in your image, and then series of different type of approaches to build prior representation in your image that will be invariant and that can be built by knowing one type of model shapes or several of them. So I started to look at a well-cited paper, the paper from Daniel Kremer and co-authors. It was a 2D approach that fixed position and scale of objects, or that tried to normalize objects and compare them with a fixed position and scale. It looked very elegant, and then I wondered why, instead of only looking at position and scale, they did not try also to have a more general pose. I mean, rotation in the object. And I just found that that it's because it becomes seriously more complicated. It looks very elegant, but suddenly you have a higher degree of complexity. So I said, okay, I did that with one of my PhD students, Jakob. We tackled the problem in a bit brute force way, and we managed to obtain segmentation where I would have some nice shape priors that would be not only invariant to scale, position, but also to rotation. So I have a similarity, Euclidean similarity invariance. It turns out that though we had the correct algorithm, our mathematics were dubious. They were wrong. They were not deeply wrong, but they were wrong, and it took a bit of time for me to realize. Also because they were very badly written. So I was wondering myself, what did I miss into that? So in this talk, I don't promise you wonderful results and plenty of very nice images, but it's a bit of trying to explain, I mean, how you do that and what type of ingredients you should do if you want to build these kind of things. So first, I mean, the general ideas that people have used to try to enforce invariance to certain type of deformation in shape priors. And then after that, I will introduce a method that allows us to build invariance by using similar and though at the same time very different property called equivariance. And then it will lead us to use as some very classical mathematical construct from differential geometry and algebraic geometry. Here, that will be in the sense of something that we call denormalization normalization, and then I will give you a couple of examples. So if I want to compare objects, then typically I start by having some sort of distance. The most classical distance in segmentation that you would have here would be to be some sort of L2 distance or LP distance between objects or the characteristic function of these objects. They basically boil up to computing a symmetric difference between two objects. And for me, objects will be some sets in R2 or R3. So here you have a function that computes distance between two objects via the characteristic function, and it's also already very clear that there might be a nice distance if you have enough restrictions on the type of objects, but this distance will definitely not be invariant to classical linear and affine transformations. So something is missing there. But what I want is an idea of pose invariance. I don't want something much more sophisticated than that now, but at least something about position, scale, rotation, and maybe I could have shear, depending on the type of imaging material I use. So in general, I would like my group of transformation, I would like to be invariant to be a subgroup of the special affine group. The special affine group is the group of affine transformation with linear part having positive determinant, because I don't want to have reflections. So I'm allowed to turn, scale up, scale down, move, but not take a mirror copy of my object. So classical things I can look in this group of transformations, there would be just translations themselves, homotheses or scalings, positive scalings, because I don't want reflection. Scaling and translations, that was actually what was used by Daniel Kramers in his talk. Very general way of talking about pose invariant is normally implying rigid transformations. I mean, the special Euclidean group. For me, I mean, it's very clear that I want the special Euclidean similarity. So I want rigid transformation and scaling, and I could also take larger groups. So the question that it takes is, what is a shape to us? Shape is has a lot of definitions, but we should probably agree on a definition of a shape if we want to implement it. So the first attempt to have an operational definition of a shape for mathematics and computer science was probably made by David Kendall in '84. And for him, it was all the geometric information that remains when location, scale, and rotational effects are filtered out from an object. That's essentially the type of information that was also used by Coutts and Taylor. So Kendall defined some spaces, and they were essentially the objects modulo the group of Euclidean similarities. So in that case, Kendall objects were made by discrete set of points that would describe the boundary of these objects. To us, there will be a class of objects modulo some of the groups that I've listed above. And I've used the word object in order to try to not to confuse it with shapes. And the object would be the basic object, the basic element that I want to use. And that will be, for me, essentially a compact connected subset of R2 or R3 with non-empty interior. And maybe I could also add an extra hypothesis on the type of boundary if I want to be able to compute with it. On these objects, then the affine group of Rn of R2 or R3 acts basically by moving each of the points, and they make the nice actions on this object. And I will also recall you a bit later what I mean by action and the group action. Just for now, I mean, I will consider a shape what remains when we have factored out scale, translation, position, and rotation in terms of mathematical terms is basically taking all of them at the same time. That means I not only consider an object, but I consider all its possible translation, rotation, scaling. And this big set of all this transform object, it's called the orbit of this object for this action. And the shape is one orbit. I mean, it's a lot of objects, but it's also one special set, this orbit. And the set of all these orbits is called the quotient set. So the set of all the orbits for the transformation from set X by this group is the quotient set. If I want an invariant shape function, so a function that goes from objects to R, for instance, what I want is something that does not change when I apply one of my transformations, and means does not change when I apply one of my transformation. It means that this function should be constant on the orbits. I mean, so it means in terms of mathematics that I can have a factorization of my functions via the quotient set. I will use once or twice a couple of these diagrams, but I'll try not to abuse it. So is it easy to construct? Not necessarily. The structure of the set of object orbits can be very complicated, actually. Not always, but it can be very complicated, and it depends on the group. So because I have no fancy images with polarization or 3D reconstruction with a 3D printer to show you, I've decided yesterday to make a few sketches on my computer. So here you have an orbit of rat shapes. I started with rat brains, but I could obviously not draw very nicely some rat brains, so I decided for rat shapes. So a couple of standard ways that have been used in order to represent this shape and use them for fitting and segmentation. So I have already mentioned the work of Kendall, where he has shaped, they are represented as finite dimensional objects. They are collection of points in R2 or R3. And on this collection of points, it looks at the action of the affine group of some of the subgroups and try to build a quotient manifold, so a representation of them. In typically shape segmentation and representation, maybe one of the first work that we know, apart probably from Coutts and Taylor, there's been the work by Leventon, Grimson, and Fojras that tries to directly put some statistical shape influence in geodesic active contours. What he uses is the idea of trying to look at a given contour, try to normalize this contour in some ways so that it can compare this normalized contour to something it already knows. And when he has this normalization, he will try to denormalize the contour knowing the things that are in the image and then make the comparison with what is in the image and have an evolution of that. So I have already cited the work of Daniel Kremers and Osher and Soato, where they also had some sort of normalization of the object. So they built something shape prior by normalizing a representation of a shape. A bit more recently, there was some machine constrained active contours that were made in some sense by denormalization. So having a nice normalized contour and then computing some parameters and denormalizing this contour and trying to compare it to what is seen in this image. You have always, in that spirit, decided that you should kind of normalize your object, compare it to some reference, denormalize it, or take the opposite way. People have also tried to do almost direct optimization over orbits. So take an object and take all this potential transformation and build a function which is given by, say, take the object that minimizes the distance to a given object and use all the possible rotation, translation, scaling for this object and compare. And then get the optimal translation, rotation, and scaling that would minimize my distance. That was the approach by Fussenegger and Derich and Pins. There's been also people have tried to represent shape implicitly by taking series of features. That would be a bit like the eigenvalue representation of this morning, where you extract these features and then you compare these features to some features that you have already learned somewhere. They are typically the features that are taken are shape moments, so integrals of volumes and generalized volumes of these shapes. So in this talk, I will explore actually what happens between denormalization and normalization, and decided that invariance can be given by first looking at equivariance. So I will define a few things, or record, because I think most of the people should probably know them or have learned them. And I will explore a bit what it means, I mean, to be able to build this normalization, denormalization. So a few generative facts. When I talk about transformation, group, and actions, what does it mean? I said that I have a group is acting on a set. Means that I have a given group, I have a set X, and then I have a mapping from G times X to X, and this mapping gives me what I call the action of an object or transformation G on an element of the set. What I ask for it is that if my G is the identity of the set, then the resulting mapping should be the identity mapping. And that if I compose two of this action of mappings, then it would be the same as the mapping obtained by the product of my elements of the sets. And such a set with an action is called a G space. So having a set with an action, then I can consider one element of this set and then all its images by actions of all the elements of the groups. This is what I call the orbit or the G orbit of my point. What is also very interesting is that I can consider the element of the groups that let fix a given point X. That means I apply my transformation G to X and I get X. This set G of X is called the stabilizer of X, or isotropy subgroup of X. It's a subgroup, and in some sense it represents the self symmetries of X. It's fairly easy that, first of all, to check that it's a subgroup, and that if I take the isotropy group of the element G of X is related to isotropy group of X by an operation which is called conjugation. The next important stuff to me here is that if I have two J spaces, then I can define maps that in some sense conserve the structure of being a J space, and they are called equivalent maps. Means that I apply a map to an element G of X, and what I will have G of F of X. So such a map is called an equivalent map or G map. Something which is also important and fairly easy to prove is that if I have such a G map and then I have the isotropy group of a point X and then the isotropy group of the point F of X, then you will have a very simple relation that G of X is always included in G of F of X. That's one liner, but what it means is that if I, some sense, extract feature from a given X, then I will potentially add symmetries but never remove them. Means that the F of X might have more symmetries than X itself. So now, I mean, I have mentioned that most of the approaches that people use when they want to do segmentation or object representation is to be able to compare the object to a normalized form of this object. The normalized form of this object means that now I have an object and I have the orbits of that object, and a normalized form would be choosing one particular object in this orbit. Choosing one particular object in this orbit, this class of object, will means that I'm able to go from the orbit set to my set X via a map S, which is called the section of the, this map is the orbit map P of X, and S is a section of it. Means that if I have an orbit, S will give me a special point, a special representation in that orbit. And that's really a special representation, because if I take the orbit of my special representation, I'm back to where I was. and choosing a normal representation of objects in a set where I have this G action means that I would like to be able to choose unique representative per orbit. So I would like to be able to define image of maps so that I would have, for instance, S1 will be a subset of my set X, would have the property that it cut each orbit once. So if I have such a representation, then I have my own new canonical way of choosing an element. And so I know if I want to compare shape X to a given element, then I will have to normalize that shape to this corresponding unique element, and then compare it to what I know, things that are already normalized. Can I find this such mappings? There's something that from the set of orbits gives me unique representatives. So in terms of pure math, yes, always. I think actually it's equivalent to the axiom of choice. But I mean, constructing one, that might be more complicated. And can I find a nice representation? Means for me, if I want to build some optimization algorithms, then I would have something which is smooth in some sense. And finding this kind of nice canonical representation, which would be smooth, it's not always easy. It's not always possible. So, but right now, assume that I can do it. And I assume that I'm in the following situation, that I have a set X. I have the objects of interest for me. That would be, for instance, my objects that I want to compare and segment and find. And I have an equivariant map from my set of objects to some features extracted from these objects. And not in X, but in Y, I'm able to compute canonical representations of the classes of objects or the orbits in Y. So it's where my thing becomes a bit abstract, is that for each set, for each element in X, then I'm interested in finding the transformations, the general transformations in J, such that my feature that I extract from a given X, but I apply J to X, and I obtain normalized features. So taking an element, say taking a subset of R2 or R3, extract some measurements of it, and knowing that I have a way of having normalized measurement for this object, find all the transformation of my object that will give me normalized measurements. And all this transformation for a given object, I will give the name n of x. So n of x will be a subset of my group of transformation. And this group of transformation will have the property indeed of transforming and normalizing the features that I want to that object. It's relatively easy to show that n of x satisfies a simple relation. That means n of g of x is equal to n of x composed with the g-1 transformation, the inverse transformation of j. And once one realizes that, then I can build actually some functions. So give me, if I have, for instance, a functional that goes from my object set to R, then I can build a new function, this L, so curvy L, that takes my element X and compute all the potential transformation with this normalizing G and take the infimum of it. And it's a one-liner to show that this new mapping will be G invariant. It's actually what Kremers did, and I will show you that a bit later. So I try to say that in kind of words. So you have a complicated set, G acts on it. You have equivariant features on that set. You can normalize these equivariant features in a unique way. Then you look at the objects that you have in X together with the normalization that gets from Y, and then it's what you will use in order to build your invariant mappings. So once you have this kind of things, then you can probably try to build this invariant shape priors. For instance, I mean, if I have one training shape that I've normalized to some certain features, then I will be able to compute some sort of distance between a given object to my training shape by saying, now I want to take the infimum of my distances from transform object A to my transform object B. And what I do is that I normalize my object A. For instance, I will normalize my object A by normalizing its volume, normalizing its position. There could be normalizing some rotation information. But I might have different ways to normalize volume, position, orientation, and that will be reflected by the fact that I have different type of transformations here. If I have multiple training shapes, then I can basically, I mean, create J-invariant shape priors by adding them or by using more complicated configurations like this one, which means this is essentially some sort of a kernel density estimator for my shapes. So if I'm back to my normalization or my optimization problem, so I have now a feature map. And then I want to build an objective function that goes from X to R using this feature map, so that this objective function will incorporate something which is invariant via this feature map. What I do is that I have, for instance, a data term that I would have, and then I have this group invariant shape regularizer that will be built by a function that I can normalize that way. And I want to optimize it. So say I have some sort of differential structure on X, I have on Y, I have on the group J, but something is not completely enough. So first I have to be sure that I have nice features. And here you see that in this optimization problem, I have something interesting, is that I want a minimum over object A over X of some classical term, but my second term is built as an infimum. So it's a result of an optimization problem itself. And in this optimization problem, what I have here is that I'm optimizing over a set that depends on the argument A itself. That makes my life a bit complicated. So I want to be able to find the infimum of a function L g of X when J depends on X itself. And it's here that the concept of denormalization and normalization appears. That's a bit more of abstract thing. So imagine that I have some sort of nice canonical representation of objects or features. How do I, from this canonical representation of features, I have all the features that are in the same orbit? It's fairly easy. I take all the potential transformation of my groups, I apply them to my normalized feature, and then the result will give me the denormalized features. So in some sense here, I have my group. It will be acting on the normalized features, and the result will be the denormalized features. So here I write it. So I take an element, a normalized feature, and I apply this element to this normalized feature. For technical reason, I take -1 because it's easier to write down. If I take the inverse image at a given point, is what I call the fiber of this inverse image. And what this inverse image gives me, it gives me all the transformations J that take its normalized features and send it to its denormalization by G-1. And this is why I introduced the G-1, because now it says that it takes all the transformation J that look at a potentially unnormalized feature and send me the normalized version of it. It turns out that these J's are essentially the ones that I used before defining my set N of X or M of X. So M of Y that defined here would be essentially the set of transformations that normalize an element. So I have denormalization going from a normal form to any kind of form and the inverse, local inverse of the mapping will be denormalization. And this actually is something which is used absolutely everywhere, but never said and never written in this kind of approaches. So the nice situation that I have myself would be the case where the group of transformation that I have is a nice compact or locally compact Lie group. It's acting on a manifold and my action is proper. So it has a definition. It means that it's a continuous and nice action in some way. And then it would be very nice if my normalized feature representation in Y would be a smooth submanifold in Y, because then I can make also use this smooth structure to make optimization. It's in the nice case, what would happen to me is that I will assume that I have this nice normalized procedure, normalized type of objects, and then each object in my normalized version possesses this group of what I call cell symmetries. It's my isotropy group. And then if by chance this isotropy group of each normal element is the same, then I'm in a very nice situation. It's something that will happen actually generically in many situations. So if I have the fact that each normalized element in my represent have the same isotropy group, then I can show that my normalizing transformation, I mean, they will all be translation of my isotropy group. And then there will be a map, a locally map that will take a generic transformation, and that will give me locally a way to choose one unique normalizing transformation in a local way. And if I have that, it means that my my minimization problem, the infimum over G belonging to n of x of this L G of x, where I have these strange things that I'm minimizing over a set that depends on the argument of the function I'm trying to minimize, then I can rewrite it as a minimization over a fixed set H, and then I have to have something a bit more complicated on my argument. If I can do that, then I'm in and I can make my minimization. And actually, does it exist? Not always, but in all the cases I will consider, then I will at least be able to find maybe not a global set that will represent all the orbits here, but at least a subset of the orbits that are nice. So I think I will skip this idea of slices. Slices is this idea of finding this nice normalization stuff. It's a bit technical. What you really need to know is that they exist. And then you have some very nice slices, especially when you consider objects that have minimal amount of self-similarities. And then they are linked to some classical constructions that are called fiber bundles. So for me, the slices, this fiber bundle, I will come back what they mean with my slices. A fiber bundle is a classical object in differential geometry. It's something that looks locally like a Cartesian product, but that may be globally a Cartesian product, but maybe not. So a cylinder, for instance, is a fiber bundle. It's a trivial fiber bundle. So I would have a base, which is a circle, and then the fiber, which is essentially the segment -1, 1. A torus is a fiber bundle. The base will be a circle, and then the fiber will be another circle. When I make the product, I have something which is topologically isomorphic to a torus or diffeomorphic. The Möbius strip, for instance, is a non-trivial fiber bundle. So if you look very locally, then you will have a base, it's a part of a circle, and then it will also be the product with something that looks like an interval -1, 1. But globally, it's not the Cartesian product by this circle S1 and -1, 1. Here you have a classical helicoid structure. It's actually also a fiber bundle, and the fibers are discrete here. Over each point on the base, I have a discrete set of points, and the same, more or less, if I change the point, then I would have also same type of set of points. So a fiber bundle, what it is, you have a base point, and over each base point, you have a copy of a fiber. Fiber bundles, for me, will be a base that would be a subset of all nice normal representations of my shapes. And above each point of this subset, what I will have is a copy of the group of isotropy of that shape or that representation. And it turns out that it's it's the basic object. So when my shapes or the the features I extract from my shapes show a minimum amount of self-similarities, then if I group nicely all the normalized shapes in a subset and then put all the, for each point over each normalized object I put is modified group of self-similarities, I would have a fiber bundle. And it's exactly the things that I need to make my optimization. So, and the fiber bundles I'm really considering here, so it's the slice, so normal representation of features, action of the group, and something that goes from denormalized back to the group. So this denormalization and normalization. So I have something which is called a projection and a section. So yet I used section a second time. They are not exactly the same as the section as before, though actually they are also in the sense section of a projection map in the sense that they are their right inverse. So I don't want to go too much in the details, but once you have that, we can write, as I already mentioned, the minimization of our invariant shape priors in a nice way. So now it's interesting to look at some examples. They are probably a bit more speaking that the general nonsense I talked before. So I start by using the group of scalings and translations. And the features I'm interested in looking at, they are scales and positions. And the group of scaling and translation, it will act on scales and position by multiplying the scale by the scaling factor and translating the position of my object by the translation vector. So it's written here. So I have a scaling translation transformation that will act on the scale position pair by multiplication here, multiplication of the scale by the scaling, and then multiplication of the position by the scaling factor plus translation. This group action is very simple in that case. It means that it's a transitive and free action, means that to go from any scale position object to any other scale position object, I have exactly one of this scaling and translation transformation. In terms of group and group action language, we say that the manifold of scale and position is a principal homogeneous space of my group G. Here I have only one orbit because it's a transitive and free action. It means that I can go from one feature to any other feature by a group action. So it means that all my features belong to the same orbit. I have only one and they belong to the same orbit. So finding a normalized representation, in that case, it's very simple and I have no problem at all because I just have to choose one point in this orbit and no more. So choosing one point in this orbit and I will have my slice or section or normalized representation. So I will simply choose the one for which the scale factor is 0 and then the position, the scale factor is 1 and the position is the origo. So now I want to build a feature map that takes an object and then extract something related to scale and position. And so that this feature map will be equivalent. So the simple thing that I can do is that I can take the barycenter of my object. And then I will here extract a scale measure of my object by computing a second order moment, basically computing a covariance of this object. So my object is a set in R2 or R3. And then I have this covariance matrix, and then this scale will be defined as the square root of the trace of this covariance matrix. So that gives me an idea of a spread of my object. And it's very simple to see that if I transform my object by scaling transformation, what I will get here, I will transform the barycenter of my object by scaling and translation, and I will transform the scale by the scale factor of this object. So it means that I have an equivariant mapping. And now if I want to find a transformation of my object that normalizes the scale and the position, means that I will send the scale of my object to 1 and the position to the origo, then it's very simple. I take my object, I subtract its barycenter, and then divide by the scale, and then this new object will have scale 1 and barycenter the origo. And if you believe me, that means that the transformation that I have here, or the function that I have here, that takes an object A and compute, say, some moment or whatever distance, not from A, but from A minus is barycenter and divided by the scale, then I would have something which is automatically invariant by translation and scaling. That's actually the approach that was taken by Kremers, O'Shea, and Sowato. If I look at what I call the normalization denormalization bundle here, that's a very, very trivial bundle. I have 1 point in my set G, in my set S, and I have the group action. And then because I have one very point, I have nothing to do. And that expresses, I have no minimization, no infimum here. I have nothing to do. The object I want to minimize over is very simple. So if I want to do the same trick, but so I take the same features, I mean, position and scale, but now I want to use them to build something which is invariant by scaling, by rotation and translation. So it's fairly easy that defining an action of these features by saying multiply the scaling factor by the scale, and then taking the position and then scaling, rotating the position, adding the translation, make a nice action on these features. Now, if I'm looking at orbits and translations, I mean, I want, for instance, to know how many transformations will send a given position, scale position to 1, 0. So scale 1 to 0, then I will have many transformations that will send scale position to 1, 0. And all the transformation that will send the scale position to 1, 0, because I have introduced rotation, they will actually be parameterized by my rotation group. So what that means, it means that the features that I've chosen here, scale and position, they don't convey any orientation information, and I will have to pay the price somewhere. I will have to pay the price that if I want to define by my invariance by equivariance, then I will have suddenly to have to run an infimum over something which is much larger. My set N of A, so my subset of transformation will be something which is a translation of the rotation group here. And that will be a bit more complicated to compute an infimum of that, and therefore having this group invariant shape regularizer if I want. So I should introduce some features that can read things about orientation there. The simplest way to introduce things that can read orientation would be, for instance, not to have just the trace of the covariance matrix of square root of the trace, but take the entire covariance matrix. And that is fairly easy to see that similarity transform will act on the position and this covariance matrix by basically similarity transforming the position and then transforming the covariance matrix by the scale of my similarity square times rotation, similarity, rotation, covariance, rotation transpose. That's something that can be done fairly easily. Normalized representations for that, a classical normalized representation for this object would say position, take to the origo, and then the symmetric positive definite matrices, then represent them by some diagonal matrices. So, and I would like to have a unique, nice representation. I would take diagonal matrices, and I would take the eigenvalues sorted in decreasing order. And if I want to get rid of the scale of this object, that I will impose that the sum of the eigenvalues is 1. So if I use that, and I'm trying to understand what is for these normalized features, how each orbit look like. First of all, I will say that my normalized feature will cut this orbit exactly at one point, this normalized point, but orbits will be vastly different depending on what happened in lambda. And then I will see that by this stabilizers or shape symmetries of the element 0 lambda. The group of cell symmetries of my element 0 lambdas will actually depend on the repeated patterns of eigenvalues in lambda. So if I have no repeated patterns, that would be very simple. And if I have repeated patterns, then I would have actually some large rotation groups that will appear in the stabilizers. And another nice drawing that I did yesterday to illustrate it, that's fairly easy to see. Here I have an object. The ellipse would be will represent the variance matrix that I have. Because I take a variance matrix, that basically I have two ways of normalizing this ellipse or this object. When this ellipse and that one will be identical, but what happens to my object, then I will have inherent symmetry, 180 degrees symmetry here. I would have two of them. And if my object has a covariance matrix with repeated eigenvalues, that means that I will have some sort of circular symmetry here. So here I would have two ways of normalizing it. Here I would have infinitely many ways of normalizing it. So two ways of normalizing it, then I can actually, for general ends, then instead of two ways, I would have 2 to the power n-1 ways, and they will be described by a given subgroup of my group of rotations there. And then if I use that, then I can use it to build for objects that do not show any circular symmetries, then I will be able to build similarity invariant functional for my objects by saying I take one of the potential normalization of my objects. I take this object minus this barycenter divided by the shape, but one of these representation normalization of my objects, I should not only consider that one, but also consider possible other normalization. Like here, I would have that representation or that one. So my P would say me how I can, go from one representation to several of them. What I will ask for my one of these transformation is to diagonalize my covariance matrix. And then I would need to minimize this kind of thing. So the interesting thing is that here my group is discrete, that if my L function here is continuous in some setting, then I will be able to show that this minimization, so if I start at a given t time it equal to 0, and I have known a p that will let me to give this, that will give me this minimum, then by a small evolution in time, then this one, I will have a nice way to compute it, and this p will never change. So it means now that even though I have a minimization, I know that at least for a small step of time, I can get rid of the minimization and just have something that would depend on my shape object in these moments. I can always do it when my stabilizers or normalizations are finite. That's exactly what I used here for building the segmentation of these brains and also the things that we are building for these femur bones. So this one are some of the last images, and it shows that it works. And here we can start something that is a bit far away in terms of shape, or at least in scales, and a bit rotated, and then we will go and we will converge to something nice. I don't know how much time I have left. I think I'm probably close to being done.
Francois, you should go quickly.
I think I have only this slide and the next one, more or less. So scaling in position, I showed you that it's basically the approach of Kramer's. If your group is the group of scaling and translation and your features are scales and position, then it's fairly easy, I mean, to write down this kind of invariant transformation through this process. What is interesting is that when I have scaling in position and my group is scaling and translation, then my group acts on my features. It's a way that is called the faithful action. It's a nice action. When I have similarities, what I did with similarities actually to build my transformation was take my object and try to set a Gaussian transformation, a Gaussian distribution. So I take my object like a uniform distribution or uniform density function, uniform over my object, and I try to approximate it with a Gaussian distribution. And the Gaussian distribution has some inner symmetries, and I have to pay the price for that. I could get some new features by having something which has not the inner symmetries of a Gaussian, and that might be able for me to remove some rotation ambiguities. But I would probably have to pay the price in terms of building this kind of functions. I can also modify the features. Maybe if I add more features, that I will decrease the amount of symmetries and have something nice. But again, I mean, I might have to pay the price in terms of segmentation. So just a short conclusion. So I have made an attempt to understand some of the principles when you use, when you want to design invariant shape priors or invariant to some group actions. I proposed some sort of recipe to building them via some features extraction that are G equivariant. It's linked to classical object of differential geometries. It's still limited in the use in printing, 3D printing now, apart from femurs and rat brains. It might be used in computer vision and medical imaging with more complicated features. And for infinite dimensional groups, it might be used, but that will be probably a bit more complicated. Just one word is that this object that I've mentioned, this fiber bundles and principal bundles, actually there were two of them yesterday in talks, the one from Giuseppe and probably one of them by Adrien. They were there. They were never mentioned because probably you don't know they are there, but they were there. And that's it. I thank you for your attention.
Okay, thank you very much for your interesting talk on applications of geometry in algebra to segmentation. So I do not see hands. Is there anyone who would like to raise some questions or comments? Well, I have one, and it's related to the techniques you use to make segmentation. Because usually there are mathematical techniques or numerical methods to segment an image, which are related either to variational techniques or level sets or PDEs or threshold techniques. So in this case, when you want to use your approach to make the segmentation in one image, so which kind of numerical methods do you use?
So typically here, the technique was level set based or trying to have representation by label functions. I mean, characteristic functions. But a nice way to do it and to deal with that is fundamentally to write it via level sets and derive evolution equations from all these things. So when you go to level set representation, then you will have you will end up by having some level set evolutions. No, continue, Maurizio. Sorry.
No, but then you have to solve several evolutive PDEs, or I don't understand, because you are considering also rotations or other translations or affine transformations. So every one of those corresponds to a different shape. So by the level set method, you can segment an image according to the level of grays or level of colors.
Yes.
But now, if you are looking for a prior, I don't see how you can adapt the method. Perhaps I'm stupid, but I don't see how you can adapt the level set method in order to find a specific prior.
But so first of all, of course, to the segmentation, I would have first a data term. So this one was written, it is something that looks a bit like the Chanvese data term, except that it's using local means, not global means by segment. But the prior by itself, my object A would be represented by an evolving level set. And I can rewrite all my equations in terms of this evolving level set function phi. Or actually what I would do, and what I did was not to rewrite everything directly, but to use shape derivatives, classical type of shape derivative terms, and then compute the shape derivatives with respect to these terms. And then when I have the shape derivative equation, I have the classical dictionary between shape derivatives and then vector fields along the contours of the shapes, and to translate it into some level set evolution.
Okay, thanks. So are there
no more than that?
No. So if this is not the case, so we are going to take the last